Hello, this is Brady Chen. Welcome to CSC7013, Advanced Math for Computer Scientists. Before I start the class, let me first introduce the Computer Science Department under the Fitchburg State University. The Computer Science Department has 7 full-time faculty and 6 adjunct faculty. We offer 3 programs, 2 undergraduate programs and 1 graduate programs. The 2 undergraduate programs are Computer Science and Computer Information Systems, and sometimes we call it CIS. Now the graduate program has 2 versions. One is regular face-to-face program. The other one is the online version. Now also the Computer Science Master's program has a data science concentration, which basically provide some courses dealing with the big data and the data analyticals. Now, what you are seeing now in this slide is the building called Adgley Hall, which houses the Computer Science Department. So if you have a chance to visit the city of Fitchburg, please stop by the Fitchburg State University, stop by the Computer Science Department. Now Fitchburg is about 40 miles west of Boston, so if you happen to be in Boston area, just feel free to visit the campus. Okay, I think let's get back to business. We will organize the class into modules. Now each module covers a specific area in math that will be used in computer science. Now the first module, the module 1, is about the Boolean algebra. Now here's the learning objective for module 1. So we're going to talk about the truth tables in module 1, and also we're going to talk about the De Morgan laws, and then we're going to touch a little bit about the theory of proof, and we're going to show examples of how to prove certain things by contradiction. And then we're going to actually provide some of the examples of demonstrating logical equivalence with truth table. Now the fundamental part of the Boolean logic is something called a proposition. Now by definition, propositions are the theorems of our language, and they are to describe or denote what is the case. Let's see an example. So suppose we have a statement, say Paris is the capital of France. Okay, now this is a proposition, and I can say this is a proposition 1. Okay, now a proposition has a value. Now it's either has a value truth or false. Now what is the value for proposition 1? Paris is the capital of France. The answer is, of course, the answer is truth, right? But sometimes a proposition has a value false. For example, we have another statement to say proposition 2. Okay. Now we can say New York City is the capital of the United States. Is that true or false? Now the answer is it's a false. Now, so this proposition 2 has a value false. So if a proposition describes something which is the case, then it is a true statement and the value is truth. And if not, and it's a false statement. So now we know what is a proposition. A proposition is just a statement which has some value, either true or false. Now, people are more interested in knowing how to create a new proposition from older ones, and typically a simpler ones. Now, in order to do this, we need to define some of the logical operations. These logical operations are sometimes called logical connectives. Now here, we have 4 logical operations: conjunction, disjunction, implication, and negation. And the conjunctions are sometimes called and the disjunction is sometimes related to or. And implication means that if something happens, then something else happens. And negation means not. Okay. Now, we also use for math notation to represent these 4 operations. The conjunction, we typically use the notation like this, and disjunction is like this, and negation and implementation, we use the arrow. So let's take a look at the examples on how to use the simpler proposition to build a more complicated one. Now let's take a look at a statement. Okay, so this statement says it is not the case that John is married and John's wife is not married. So it looks like this statement is very complicated. So how can we write this proposition using the symbolic form? That means we start from the simple proposition and using the operations to build this complicated proposition. Let's assume that the A stands for John is married. So it is a proposition, right? And it has a value. It has a value. It could be true or false. Okay? And then B stands for John's wife is married. So this is another proposition, another statement. Now these are simpler statements. So looks like if you compare these top one, looks like this is actually simpler one, but somehow they are related. So looks like A and B are the building block for this more complicated statement. Okay. Now with A and B, how can I build this statement? Okay. So we have 4 operations: conjunction, disjunction, negation, and implication. Okay. So now in the statement, it contains a small portion says John's wife is not married, but B says John's wife is married. So how can we build this, small portion using the proposition B? Okay, the difference is very trivial. John's wife is married, that's B. But so looks like we can use one of the operation called a negation to build another statement. That's John's wife is not married, right? That's part of this bigger statement. So then we use negation. Okay. So negation of B, stands for John's wife is not married. Now, then we can actually combine the A and negation of B to build a bigger statement, a big proposition. So we can use A, conjunction, negation of B. So this conjunction is actually basically means and. So this is basically stand for John is married. That's A, right? And that's the conjunction. John's wife is not married. Okay, so that's negation of B. So A, conjunction, negation of B. So that's basically stand for John is married and John's wife is not married. But that's still not the same as the top statement. Okay, but it's closer. The top statement says it's not the case. So that means this it's pretty simple, right? This is a negation of this whole thing. So that's why the statement can be written as negation of this whole thing. Now, what's this thing? It's A conjunction negation of B. Okay, so that's the whole symbolic form. This form basically stands for it is not the case that John is married and John's wife is not married. Okay, so here we basically from a very simple proposition A and a B, and then we build a very complicated statement. Negation of A, conjunction, negation of B. Okay, so that's just one example. So now we have seen the example of how to use two simpler propositions to build a more complicated one. So, however, when we try to build a more complicated one, now the question we're going to ask is, what's the value of this complicated proposition? If the value of the simpler proposition is none. Okay, in another example, like the previous example we just talked about, so we have two statements, right? A and a B. A says John is married, and B says John's wife is married. So we build a compound statement which says it's unlikely that it's not the case that the John is married and John's wife is not married. So that's a compound case, compound proposition. Now, what is the value for this? Suppose we know what's the value for A and what's the value for B. Now, if we know A is true and B is true, so John is married, John's wife is married. And then with our common sense, looks like that's also true, right? Because the proposition inside the parenthesis says A, John is married, and John's wife is not married. How could that be possible, right? So that's not possible. So that's why if we put the negation over here, says it's not the case that John is married and John's wife is not married. That's a true, right? So that's a true statement. Okay, if that's true, and that's true. And with our common sense, that's the case. Now, but how can we use the math symbolic form to get the same result? Then we need something called a truth table for each of the operation. Okay, so we need the truth table for conjunction, truth table for disjunction, and the truth table for implication and the negation. I think the truth table for conjunction, disjunction, and the negation are pretty straightforward. Let's take a look at the conjunction. Conjunction basically means and. So in English language, and means, by definition, if P is truth, now we use 1 to represent the truth, and Q to represent 0 to represent false. Now, P and Q, that means if P is a true statement, Q is a true statement, and P and Q is also a true statement. However, if one of the propositions is false, that either P is false or Q is a false, or both statements are false, then P and Q is a false. It's kind of like common sense, right? Now, same thing with disjunction. Disjunction is kind of a weak condition. So P or Q. So that means if one of these is truth, then the whole thing should be a truth, right? So that's a weak condition. So the only case that the P and the Q are false is that both P and the Q are false. Okay, that's simple. Now look at the negation. If P is true, the negation of P is false. And if P is false, the negation of P is true, right? That's very simple. Now, the complicated case is the implication. Now let's take a look at the table. The table says if P is true and Q is true, and P implies Q is truth. Sounds like it's a little bit easy to understand this case, but that case is also easy to understand. Now people are mostly confused about this. If P is false and the result is truth, then the Q is a truth, and then the whole thing is truth. P imply Q is a truth. Now, how this could happen? And another case is like if both P and Q are false, then P imply Q is also a truth. How can we interpret this? Now let's take a look at the example. Okay, so let's say we have a statement to say if you get 4.0, so you got a very good grade for the course, let's say. Okay, I will give you a reward. Okay, I will give you $500. Okay, so that looks like an implication, right? Now let's say if I define A as you get 4.0 for the course, and the B says I will give you $500. Okay, so two propositions. You get 4.0, B, I will give you $500. Okay, so in this case, then we're going to say if A, then B. So if you get 4.0, then I will give you $500. So that's the case, like more like A implies B, right? Now, if A is a truth, so that means, okay, to make it simple, let's say P instead of A, because I want to be consistent with this truth table. So if P, you get 4.0, if that's P is a truth, the value for P is truth, so that means you get 4.0. And the Q is a truth, I will give you $500. Or both P and Q are truth. Of course, then this statement is true, right? If you get 4.0, I give you $500. Everyone's happy. So P is true, Q is true, and the P imply Q is truth. No question about this. Now, how can you interpret this one? Okay, if P is true, so that means you get 4.0, and I don't keep my promise. I did not give you $500. So that means P imply Q is a false, right? because I get 4.0, but you don't give me the reward. So the whole thing is false. Also, that's understandable. Now, how can we interpret this third case? Okay, so now P is a false. That means if you don't get 4.0, so that means P is a false, that you don't get 4.0. And Q is a truth. That means I still give you $500. So in that case, it is a false that you get 4.0. Now, in that case, whether or not I gave you $500 or not, whether or not I gave you $500, it doesn't matter, right? So anyway, I haven't broken my promise. If I gave you $500, I haven't broken my promise. I give you $500, I still, haven't broken my promise, because anyway, you failed the test. You didn't get the 4.0, so it really doesn't matter what I do. The result is always the truth. In none of the case I have broken my promise. So that's why if P is a false, so you did not keep your promise in the first place. Really, it doesn't matter whether I keep my promise or I fail to keep my promise. In either case, I haven't broken my promise. So that's basically the reason why we interpret this as truth in either case. If P is a false, then P implied Q is always truth. You get this point? So, based on the truth tables of these four operations, conjunction, disjunction, implication, and negation, we can actually get the following four facts for each cases. The conjunction is true if and only if both conjunctions are true. So that means if A conjunction B is truth, then if and only if both A and B are truth. Now the disjunction is a kind of weak condition. That means the disjunction is false if and only if both disjunctions are false. That means A disjunction B is 0, then both A and B are 0. Okay. Now the implication is false if and only if antecedent is truth and the consequent is false. So that means A, which is an antecedent and a consequent, and A is truth and B, the consequent, is false. Then A implies B is false. That's the only case when A implies B is false, is that the A is a truth and B is a false. Negation is pretty simple. It's very straightforward. Negation converts truth to false and the false to truth. Okay. Now let's talk about the De Morgan law, and then we're going to prove the De Morgan law. Okay. De Morgan law says if I have two propositions, P and Q. So the De Morgan law says the statement negation of P and Q is equivalent to the statement of the negation of P or negation of Q. So these two statements are equivalent. So that means they are exactly the same. Now how can we prove this? Okay. Now we can prove this using two strategies. One of the strategies is to using the truth table. So we can try to build a truth table for the proposition on one side, and then we can build another proposition truth table for the proposition on the right side. Okay. So then we compare these truth tables. If they are equivalent, then we can say these two statements are equivalent. Let's take a look at this example. Okay. So now here we have two propositions. So that means with two propositions P and Q, you have the combination of four cases. Now what four cases? Now either P is true and the Q is truth, and the P is a truth and the Q is a false, and the P is a false, Q is a truth, and both P and Q are false. So these are the only four cases we can think of. Now, in order to calculate the values for the statement on the left, then we need to first calculate the value for the statement P and Q, because eventually we want to calculate the statement of P, negation of P and Q, but first we need to calculate P and Q. So then we use the tables for the conjunction, right? So P is true, Q is true, and the P and the Q is true. Now P is true and the Q is false, and P and the Q is also a false. P is a false, Q is a false, and the P and the Q is also a false. I think that's a mistake. I put a 1 here. And both P and the Q are false, then these are false. Now, the negation of P and the Q, that's pretty simple, right? It's just the opposite. So if P and the Q is a truth, then negation of P and the Q is false. And then these are all true. Now, let's take a look at this case. Now, if we want to figure out the values of this statement, so we need to first calculate the negation of P and then calculate the negation of Q, and then we calculate the OR, the disjunction. Okay, so P is true, so negation of P is false, right? Q is true, negation of Q is false. Now P is true, negation of P is false, Q is a false, negation of Q is a truth. So it's just the opposite. So it's a 1, 0, and a 1, 1. And then negation of P, disjunction negation of Q. So both P and Q are false, so the disjunctions are false. And then even if one of these negation of P and the negation of Q is truth, then the result is a truth. So now we find out the values for this and the value for this are identical for each of the case of P and Q. So that means we proved that these two statements are identical. So we actually summarize our proof in this slide. So we actually put the two statements. One is A, one is B. We assume the negation of P and the Q is 1, which is truth, and the negation of P, disjunction, negation of Q is 0. If we assume A is 1, the B has a value 0, and then we actually get the contradiction. Okay, so please take a look at this slide. That's exactly the process that I actually proved in the previous slide. So here's the part B of these proof by contradiction. Now if we assume A is 0 and B is 1, now how can we get the contradiction? So that's your turn. So now here's another example of proof by contradiction. Okay, let me actually briefly summarize these proof technique. Okay, let's say we want to prove this statement that is logically false. It's always logically false. Now, you can actually use the truth table. There are two propositions, P and Q. It's there's two propositions. There's 4 possible combinations. P is a truth, for Q is a truth, P is a truth, for P of Q is a false, and P is a false, Q is a truth, and P is a false, Q is a false. There are 4 possibilities, and then you can build a truth table and then show that the truth table always get the false result. Okay. Now with the proof by contradiction, then we just need to assume that if this statement is not logically false, okay, so let's say assume this is true, okay. Now we try to use all the facts that we listed in the previous slide, and then we can just show eventually this is not possible. Okay, so the first thing we need to do is, if this is true, and then because there's a negation, by definition of a negation, then this is false, right? From 1 and definition of negation. Okay, 1 basically means this. Okay. So if that's the case, and then this is 0. Okay. Now the next one is we have this proposition and this proposition. Okay. So this is implication, right? If the implication is 0, so that means the first part must be truth and the second part is 0. That's basically by the definition of implication, right? So we remember that here's a P and a Q, and if P is 1, Q is 1, then result P imply Q is 1, and if P is 1, Q is 0, that's 0, and 0, 0, 0, 1, 0, either one is 1. So if P imply Q is 0, that means P is 0. P is 1, Q is 0. And in that case, the P is this compound. P is this compound proposition. So this first part is 1. The second part is 0. Okay. So Q is 0. And P and P implies Q equals 1. So that means P and P implies Q equals 1. That's a conjunction. So if this is a 1, that means both P and the P implies Q is 1, right? Because that's the definition of conjunction. Okay. From 3 and the definition of conjunction. So P is 1 and the P implies Q is 1. So then, just remember, we actually get from 4, P is 1, and P implies Q is 1. In that case, and so Q must be 1, okay? Because if P implies Q is 1, Q must be 1. If Q is 0, it doesn't matter what the P is. The result is always 0. So if this is 1, the Q must be 1. Now, what's the problem with this result? Because previously in step 3, we find out Q must be 1. If we assume this is 1, Q must be 0. And then we say Q must be 1. How could that be possible? One says Q must be 0, and the other says Q must be 1. That's a contradiction, right? So there's a contradiction between 3 and 5. 3 says Q must be 0, and 5 says Q must be 1. And that's a contradiction. Now, the reason we got a contradiction is because our assumption is not correct. Okay, so the assumption 1 is false. If the assumption 1 is false, that means this is always going to be false. Okay. So, okay, that's the last slide for Module 1. In this slide, I want you to prove that these two statements are equivalent. And I want you to prove this with the truth tables. Actually, I already provide you with the truth table. So you can actually pretty much verify this. And if you want, you can also use the proof by contradiction. So in that case, just keep that in mind. If you want to prove the equivalence of two statements, you have to prove two possible cases. One, we assume one is true, the other is false. Okay, so like this is true and this is false. We assume this, and we actually get the contradiction. And then we need to actually also assume that if this is a false, this is true, and then we got the contradiction. So that means either case is not possible. Then we actually proved that the two of these statements are equivalent. But for a truth table, we just build a table for each of this, and then we can prove it. I think that's pretty much all for the Module 1. See you later.